Okay, thanks folks for coming. Thanks to people on the Zoom for coming. I'm really happy to be here. We had a really nice dinner last night. It's a whirlwind trip. I'm so happy that I made the trip. As Misha mentioned, I work on a pretty broad spectrum of things. It was when I started postdocing that I started getting really interested in dark matter. That's partially because I think when you start postdocing, you think about like what's the most important work that you can be doing, and you also need to take risks. You know, the default path would be you start postdocing and you don't get a faculty job. So if you really want to, you know, make your mark and then end up being academia permanently, I think you need to, as a postdoc, work on new things that you think will be important and high impact. So this is, you know, this is a body of work that I delved into as a postdoc. It's something I'm really excited about to this day. And it's the topic of ultralight dark matter, which I think is rising in prominence really in the last few years. And it's based on this series of papers here. Oh.
You pointed to the computer.
I guess we
Point to the computer. Right, that makes sense.
No, we just use it manually.
Wow, okay. Well, off, on. No, well, that's okay. Right, so the plan for today is I'm going to introduce this class of models known as ultralight dark matter and how it leads to a ton of interesting phenomena, which collectively you can think of as cosmological condensed matter physics, the application of ideas in condensed matter to cosmological systems. Which the ball on this really got rolling with fuzzy dark matter that was of course invented here. That's sort of the genesis for this whole field. And it's developed into something much broader and I think really interesting. So what the plan is basically to go through models and really try to demonstrate that this is a class of models. There's a question in the chat there. Okay, as I said, she cannot see the slides.
I see the slides.
Okay. So maybe recheck your settings or something. Go from gallery view to something else. I don't know. So the plan for today is to go through models and then experimental arenas where you can test these things. Which is part of what's exciting is that there's a pretty broad set of experimental arenas for testing this. Oh, works out great. And check the time. Okay, 5 after. Promise I won't go over time. We should have, hopefully if you're able to stick around after, we can have a more in-depth and detailed discussion. I'm here for the rest of the day. But so, you know, before delving into this talk, I think we all are very familiar with dark matter. You go to a seminar every week and people probably give you the same couple of slides. My one slide on this is just to emphasize that the Planck 2018 Filaments CDM can reject the null hypothesis that there's no dark matter at greater than 70 sigma, which is, you know, just mind-boggling. And so when you give, I think when you give a public talk and you try to convince people that dark matter is important to be working on, telling them that like we know with such a degree of certainty that dark matter is out there. Like this is a huge question mark for theoretical physics, for particle physics, for cosmology, for astrophysics. So this class of models known as ultralight dark matter, I mean, the origin of this goes back to axion dark matter, and before that, the idea of the axion. And there's 3 well-known papers that posited this. You can look up the references in any article. But so to a field theorist, which is my background, I come from a high energy theory background. The operational definition of an axion is that you have a global symmetry, a global UN symmetry that's spontaneously broken. So it's the it's the Goldstone boson of some global symmetry. And then this, in addition to the spontaneous breaking, there's also an explicit breaking of the symmetry through some non-perturbative effects like instantons. And that additional explicit breaking, by virtue of being non-perturbative, you still have the protection from loop corrections to the mass. The explicit breaking generates some non-zero but small mass for the Goldstone boson. And this is the idea of an axion. And because it's extremely light, the number density of particles is extremely large. So the the proper description of this is as a coherent scalar field. In the early universe, it started its potential by Hubble friction, and eventually when Hubble falls below the mass, it starts to oscillate in its potential. This is the paradigm of not just axion dark matter, but like ultralight dark matter more generally. And I think what's worth emphasizing is you have this relatively simple idea coming out of cosmology. It has implications for astrophysics, which people here know well, but it also has tons of cool particle physics. And there's a huge number of experiments from like ADMX that going after this particle physics signatures, and those particle physics interactions have signatures in astrophysical context, like huge bursts of axions coming out of pulsars, things like this. So the punchline, I have two punchlines to my talk. The first punchline is that axions were the tip of an iceberg, which is the class of models known as ultralight dark matter. And the types of things that are in this class of models is things like fuzzy dark matter, or fuzzy and ultralight fields can form a BEC in a certain context. You can also form a superfluid, which is distinguished from a BEC through the presence of some self-interaction. And you can also have superconductors, which is a close cousin of a superfluid. And these condensate states, BEC, superfluid, superconductor, can emerge from Bose-Einstein systems or fermionic systems. And the study of these types of models is what I refer to as cosmological condensed matter physics. And I'd be remiss if I didn't mention that, and the foundational ideas for this all came out of IIS. Now, my punchline number two, and this is really not the focus of the talk today, this is largely work in progress, to appear soon, very soon, hopefully, is that ultralight dark matter models are in fact their own icebergs, which is to say, if you start asking what is the complete structure of this model, there's a lot more there. And I think often we're tempted as, say, if you're doing effective field theory, to say like you have single field inflation and we ignore everything else that's there. That's like a paradigm for early Norse cosmology largely. But if you start asking what is the structure of the theory, what is the theory telling you of the signatures you should look for, there's a lot to get at. And in particular, the field of super heavy dark matter is its own field. There's a recent SNOWMASS paper. This is something at ROC in Chicago I've worked with on this topic, super heavy dark matter, has working on for many years. And if you ask like, what is the structure of ultralight dark matter, often it brings along things, new degrees of freedom and candidates of super heavy dark matter. So for example, the classic is the axion. The axion, as I mentioned, is the Goldstone boson. It's the phase of some complex scalar. The radial part of that complex scalar exists. We reduce string inflation. It's a super heavy boson, and there's observable signatures that have been developed for the last several decades for this type of field. Something that, as it is on the skull, that we're putting out imminently, very soon, is something we're calling ULP dark matter, ultralight pion dark matter, which I'm going to talk about in a few minutes. So what this brings with it is super heavy fermions, which are the dark baryons of this QCD-like theory, which is giving you ultralight dark matter. And another model I'm going to talk about, which is work I did with David Spergel and Swan Alexander, something we call STUMPs, which I'll explain what that means. This additionally comes out of my QCD-like theory, which is where axions came from in the first place. This STUMP model comes out of QCD-like theory with a very low confinement scale. And this brings additional degrees of freedom, like very nearly massless pions and couplings to standard model, like through couplings to baryons.
Sorry, I have a super stupid question, but for example, for the axion dark matter, who are we guaranteed that the heavy particle is going to be a boson? Meaning, couldn't it be like the Goldstone of some composite fermion operator?
Sure. So I mean, the ALPS is like that's
okay, so it's essentially the same thing.
Yeah, but like, what is the axion? The Petrie-Quinn mechanism is the phase of a complex scalar. But you're right, that complex scalar could itself be a VEV of so that's what we call the ULP model.
Okay, so it's really just different namings. If you call it axion, it means there's a super heavy boson.
Yeah.
Okay, thanks.
Right. So this reframing of this is called cosmological condensed matter physics. I would say it really includes these four types of models, which is first of all fuzzy dark matter, where you take a non-relativistic limit and your scalar field is described by a wave function. And under certain circumstances, it can form in a precise sense a BEC. And I should mention that itself is a highly debated topic. Alan Guth has a really nice article asking, does it in fact form coherence on long scales? But in certain contexts, you can form BEC. And there's a very nice review article by a friend of mine, Elisa Ferrero, that talks about this. And now going from a BEC, if you introduce self-interaction like lambda phi 4 necessary to have symmetry breaking, just like the Higgs mechanism, we have some Higgs potential. You get two possibilities. One is a superfluid, that's if you have global symmetry, and two is a superconductor, which is if you have local symmetry. So the Higgs mechanism is superconductivity. And if you look at the historical development of particle physics, like Leon Cooper and friends came up with a theory of superconductivity, and that led directly to Nambu developing the theory of Goldstone bosons and things, and then Higgs and friends developed basically the foundations of the Standard Model. And I'll mention one thing that's fun about this is that the study of these things really, and the combination with particle astrophysics, and really building on parallel developments that happen in particle physics. For example, the study of condensed matter physics of QCD, which is how we study neutron stars. So, I mean, this is fun for someone like me that's somewhat schizophrenic and likes and needs to work on a variety of topics so that I can just always be excited and stimulated and going from, one exciting idea to the next, which is, for better or for worse. It's worked out so far, but not for everyone. So one of the most striking possibilities in this class of models is that you get the phenomena associated with condensed matter physics. The most exotic and new to cosmology and astrophysics is the presence of vortices and the possible presence of vortices depending on your model and specific setup. And so on the right here, I just have the stock picture from Wikipedia of an array of vortices in some superfluid system. On the left, we have this artistic depiction of what dark matter halo might look like, that you have some array of vortices inside this dark matter halo. For example, the halo has some net angular momentum. If a superfluid has some net angular momentum, where is it stored? And it's stored in these defects, which are vortices. And there's a very long history. The other day I was looking at a review article by Feynman from 1955, talking about the details of this in superfluid helium. The other thing I'd like to emphasize in this talk is if we ask about what are the observables, at the end of the day, we are scientists, we want to make measurements to, you're always aiming to rule out models, reject the null hypothesis. And it's neat because there's both model independent observables and model dependent observables. So the model independent observables is things like this ultralight fields can form solitonic cores. And what is the exact size of those? Does it correspond to the core of a dark matter halo? Or does it correspond to things like boson stars? That depends on the mass of your field. But the idea that you have soliton solutions is totally generic. And the fact that those solitons are described by a Schrodinger equation is amazing and generic. You can also get phenomena, and this is something that Oliver, I don't know, maybe he's on the Zoom, has worked on extensively in numerical simulations. You generically get this phenomenon of interference. So if it's described by a wave function, you have interference of the wave function with itself. The signature prediction on one of the signature predictions of quantum mechanics. And as I mentioned, you also get vortices. You can get those one from interference at points where the density of the field vanishes, that forms the core vortex, or also if you spin up your system. So you have a halo with net angular momentum. And that's something I'm going to talk about. A recent paper we had looking at the spin of cosmic filaments, which is really exciting. And so there's also model dependent observables, such as the size and density profile of the solitonic core. And that's something which is really exciting about the ULP model, which is that you can actually get a diversity, a broad array of possible density profiles, depending on the precise mixture of pions, of ULPs that make up the halo. And also the particle physics signatures depend on what is the model. Like, do you have fermions or bosons, for example, and what is this? The construction of the model dictates the portal to the standard model. And as I mentioned before, you also have additional degrees of freedom, which are ostensibly part of the UV completion. But if you come from a perspective of someone like me, who a lot of my time is spent working on inflation. That's what I worked on with Alan when I was at Alan and Dave at MIT, and that we're still working together right now. And I've worked a lot on primordial black holes, or recently since I went to Chicago, on inflation. From that perspective, I think like we have access to the UV completion through the very early universe. Right. And that's the icebergs that I was talking about. So let's get to some models. So the starting point here, I think, where this framing of ultralight dark matter first took off was around 2015 with Justin Curry and Lasha Barazani's paper on superfluids emerging from bosonic system. And their basic idea was, if you write like the general action describing superfluid is some P of X theory, which is well known with like K essence and complex of cosmology, where you have some action that can depend on, you know, polynomial function of the kinetic term as X, as well as the field. You have some complex scalar. Their idea is you could write down some function of X and the field itself, which leads to spontaneous symmetry breaking. And so, and this, you know, the symmetry breaking leads to the superfluid state, and then you have an effective action describing the Goldstone boson, and that effective action can have can lead to things like an exotic equation of state. And that exotic equation of state can get you neat things. So the original motivation for that paper and how it was really sold, but I think it's logically distinct and need not be packaged with it, is they were looking to get Mach and things like wherein, like Tully Fisher. So what I've worked on, and as I mentioned, I started thinking about dark matter when I started postdocing, was about how this can arise from fermionic systems. And actually the genesis of how we arrived at this is trying to clone gravitational leptogenesis. So this idea goes back to Stefan Alexander and Michael Peskin. Stefan was a postdoc at Stanford about using gravity and gravitational anomalies to generate asymmetry, the standard model. So if you just clone this to dark matter, which is like seemingly trivial, what can you get? And actually the theory is pretty constrained, again, by anomalies. And what you have here is a non-thermal distribution of a huge number of very light particles. And you have these interactions coming from are in some dark QCD. We argued in this paper then that the vacuum state of this theory is actually the condensed state, which is the superfluid. And I'm happy to talk in a lot of detail about this picture and this construction. So this could, all the models I'm going to talk about are like rightfully speaking their own talks. So the goal of today is to give a more broad overview and, you know, try to communicate that there is a broad class of models which to collectively form ultralight dark matter. So next thing I want to talk about is, again, another paper with Stefan and David. And I remember this because actually the first like communication we had about this, I was at the DMV in Chicago, like in a ginormous line when we first like were putting these ideas together. And we call it, the name was David's idea, which is like a really good name, I think. Is STUMPs. And the STUMP stands for strongly interacting. There's like a QCD-like model. It's ultralight. So it's the idea of our standard model QCD as a QCD scale that's relevant for our terrestrial particle physics. But what if we took the confinement scale of this dark gauge theory to be cosmologically relevant? And it's Milli charged. That leads to the actual model construction. And part of our motivation was to connect it to baryogenesis. I'll mention that just as a brief aside. And of course, particles. So STUMP model or STUMPs. And this is in fact a superconductor. And it's making use of the phase diagram of QCD, which was developed to study standard model QCD, but it's found to be more general, which is that at high density, which is densities above the confinement scale, which has the mass of the standard model, the neutron and the proton. At densities above that, so at nuclear density, you form this condensate state. And so in our model, the picture is that the lightest baryon of the confinement scale is very low. So you have a huge number of density to conform these condensate states. And the part of the original motivation for us, and that's the M in STUMP, was thinking about portals, ultralight dark matter, connecting it to the standard model. And this is actually the first construction of ultralight dark matter, which is charged under standard model symmetries. How can you couple ultralight dark matter standard model? One way is actually through thinking about lepton number, baryon number, things like this. And the idea was, and we didn't even put forward a concrete baryogenesis mechanism, but just this, motivation that if you took a baryon symmetric universe, but you stick to the model of ultralight dark matter, what does that imply? It would imply, and if you think about, so ultralight dark matter equalized symmetry would imply the baryon number that you assign to dark matter is very small. And logic can also go the other way. What if you're really charged under baryon number? What does that imply? It implies ultralight dark matter. So what does this get you? Familiar from this class of models of ultralight dark matter can get you cores for dark matter halos. And the core size roughly corresponds to what is a confinement scale. And then you can use techniques developed for QCD, which is, you have expressions for what is the equation of state, and then you can solve the TOV equations to get solutions for solitons. And for a certain region of parameter space, you can get, a resolution of the core cost problem. And I want to emphasize, I didn't put this into the talk, but that the core cost problem was part of the original motivation for, fuzzy dark matter. But myself personally, especially as we start to move away from the WIMP paradigm, is I think that the core cost problem is and similar to how the original superfluid model was trying to get MON, these are logically distinct things. This is a broad class of model with interesting particle physics and interesting cosmology. I think they weren't studying in and of themselves, independent of is a core cost problem, explained by baryons. But at the very least, you get these solitonic cores, and depending on the size of the core, that determines are you solving the core cost problem, or is the core cost problem solved by something else?
Can I ask a question before we move on? So, like you discussed this hierarchy between dark matter and baryons, that the density of dark matter is 5 times the density of baryons. Is it something like what amount of fine tuning do you need to assume in your model to reproduce that?
The milli charge is the fine tuning in a sense. And you're looking at going from below the EV scale to the GeV scale. So that's at least a 10 to the 9 fine tuning. And that's to get, self-consistent description as ultralight dark matter, and you see below the EV scale. So that's a separate discussion. We talked about this a bit yesterday. I'm not going to get into it now, but a certain approach to constructing new models where you don't reject models because they're fine-tuned outright. You think about what's possible if you accept fine-tunings, and think about what are theoretical perspectives where this is not thought about as a fine-tuning, but appears in a geometric framework, string theory, or in a broader high-energy theory picture. And I'll mention very briefly, because I want to get to the observations, and also a final comment on the connection to Hubble tension. But there's a variety of ways that you can distinguish these stumps. So a model where it's at the fundamental scale of UV completion, where the UV completion could be accessible to particle physics even, is fermionic versus bosonic. Okay, so the final model I want to talk about is something that's coming up very soon, hopefully in the next couple of weeks, with Astrophysicists on this call. And this is something I'm really excited about. And started thinking about what, as you mentioned, what the action of some composite state. So that idea seems, you say those words and it sounds trivial, but it's actually not so trivial. And so we actually took this idea seriously. And the framework for talking about pions is you think about spontaneous symmetry breaking. And there's also an explicit symmetry breaking coming from the fact that the quarks have a mass, and this gives a mass to the pions. And one thing that's worth noting is that in the case of degenerate quark masses, what you really do get out is a cosine potential for the pions. So there's an obvious analogy from pions to axions. But it gets you new things too. So if the quarks are charged under some standard model symmetry, for example, the simplest one, most often considered, is say the quarks have some small, they're milli charge under electromagnetism in the standard model. This tells you your charged pions have some small electric charge. So now we're talking about ultralight dark matter with some small electric charge, just because your natural portal to the center model. And and you have a mass splitting, which is determined by the decay constant and the Miller charge. And now when you ask, like, what does this model predict? Well, you have this portable standard model, and then you look at a very nice paper by Rocky and Andrew Long and one or two other collaborators, where they talk about production of super heavy fermions through various portals. And that's, thinking about this portable standard model, you can produce the ostensibly heavy fermions, like so here it's dark baryons, through freezing. So you can get subdominant population of dark matter, which has its own signals, and they're all tied together by a small number of parameters in the QCD, so all the decay constants anchored to the confinement scale, which is anchored to the baryon mass.
Sorry, another stupid question, but is it possible within exclusion regimes and stuff like that to have a regime where the charged pions are much heavier than the neutral one?
Yeah.
Can FI be strong enough that?
Yeah, you have a lot of freedom.
Okay.
And that's something which is on the slide after this one.
Okay.
Right, so you can go to the deeply non-relativistic regime where you describe all three of these by wave functions, and at the leading order in the interactions, we get 3 Schrodinger equations where I'm dropping the self interactions here and the coupling between them. And then you got a Poisson equation. So implicitly, these things are coupled. These are not independent equations because they all talk to one another gravitationally. And so this generates effectively quartic interactions gravitationally. And you got the spectrum of particles, and you got interactions with the standard model. 2 of these particles are charged. One is like a regular axion. And you can also have couplings of the baryons to the standard model, like having standard model fermions or today. So the one neat science result from this paper that I'll highlight is the diversity of dark matter halos. So for example, here's a case where I think about three dark matter soliton cores with the same mass. There's the same amount of stuff in this core, but I change the mixture of the pions, and I take the pions have different masses. So this is like somewhat trivial, I would say. It's trivial, it's epsilon away from trivial observation. That if I change the mixture, which I would argue could come from environmental conditions, in the same way that we have a galaxy without dark matter, you can imagine galaxies have slightly different mixtures of which pions are making up the halo. You get different core sizes for the soliton, and as you make the ratio larger, which you have many orders of magnitude freedom in the model to change the ratio of the pion masses, you can make the core, crazy small or big, and there's different classes of solutions which are indeed stable, or at least metastable solitons. And this image is grainy, but the picture in this whole setup is that you have some condensate core, and outside of that is NFW. So I mean, if you take the condensate core and you make it parsec size, effectively all you would see with observations is the NFW. So you really can get this diversity of halos, some with kiloparsec cores, or some with parsec size core. So it sort of falls out naturally that you should have a diversity of dark matter halos if you have this model that you have at least 3 ultralight degrees of freedom. Okay, so we're halfway through, and I want you to experiment with Marinos. This is perfect timing. And so what I've worked on extensively so far is the astrophysical probes. And what we're getting to right now, in a variety of different contexts, and this has been so far sort of motivation, is to get into the neat new particle physics. The things I'm going to emphasize today is thinking about one, astrometry. So Gaia, what I can tell you about dark matter substructure. The most well-known theory papers on this topic are about constraining a dark disk, like the double dark disk universe of Lisa Randall, Gigi, and Matt Schwartz, and thinking about that in the context of ultralight dark matter models. And then you also get neat strong gravitational lensing signals, and the fact that you have the substructure of the model is genuinely different from regular WIMPs. And in particular, what if you have vortices carry some mass density, they do some lensing. And the final thing, which is relatively hot off the presses a few months ago, is thinking about there's some evidence that filaments, some of the biggest structures in the universe themselves have some net rotation. And where could this net rotation possibly come from in the context of ultralight dark matter? Because, in the non-interacting simplest case, you can reformulate it as hydrodynamics, and there can be no net rotation of the velocity field in like the simplest fuzzy dark matter setup. Where does rotation come from in a superfluid? It comes from vortices. So is it possible that ultralight dark matter can explain spinning cosmic filaments, and what would be necessary for this to happen, and the path we went was to think about vortices. And then the one thing I'll highlight is that this paper right here is with Michael Toomey, who is a graduate student at Brown, who's amazing, and he'll be graduating next year. And you should, if not hire him yourselves, tell all your friends to hire this guy. The first thing I want to talk about is astrometry, which I'm sure a lot of folks here know pretty well, and he talks about this. It's basically tracking out the motions of stars. And you can use this fantastically to track with the distribution of dark matter, both the velocities of kinematic substructure, for example, and the density of clumps of dark matter. So what got me interested in this was a colloquium given by Angela Santi at Brown, and I was just starting to work on dark matter, which is sort of, as I mentioned, like sort of a new thing for me to take on as a postdoc. I wanted to do something new, and this sort of like blew me away. That it was such a huge breakthrough. And then shortly thereafter, you also had this, and around the same time, there's some things before even if I recall correctly, there's evidence of actual position space substructure, which is clumps of dark matter. So this is the spur and the gap, which is really exciting. So I started thinking about what could be possible in context of ultralight dark matter. And this led to thinking about this question of how could you have, so there's two well-known papers that came after Gaia DR2, which looked at constraining a dark disk with Gaia. Could you try to do the same thing in the context of something like fuzzy dark matter? And so you write down the Schrodinger equation, including a self-interaction there. And you ask, can you have Disclike solutions? But then you go into this extremely well-known paper by IS people, and then you read footnote 21, and they say it's interesting unsolved problems where there's non-circle solutions to the Schrodinger-Poisson. The Schrodinger-Poisson, strictly speaking, is you neglect this term. You could just consider the non-interacting system. There's an open unsolved problem. And then this paper is by people who are much smarter than I am, so then you could give up at that point. But instead, a fellow Canadian who was a mathematician at Brown, the applied math department, we got together and with Stefan started thinking about what could be done here. And so our approach was, the conventional thing, differential equations, you want to solve numerically, you do rescalings to make it dimensionless, and we absorb the self-interaction into your dimensional rescalings. And it's really small here, you probably can't see it, but the wave function gets rescaled like 1 over lambda. And then you end up with an equation where it's, an equation where effectively lambda is equal to 1. But you've hidden it inside of the wave function, and also you have to rescale space. Because that's step 1. So this is like intrinsically self-interacting. The limit where lambda goes to 0 is not even well defined. And then the next trick we use for math, which is sort of analogous to taking a near horizon limit of a black hole in the construction of ADS-CFT, is you do, in math, they call it the far field core decomposition. I mean, it also comes from electromagnetism. You look at Jackson, he does this. And the idea was you take a coordinate system, you take this, zoom in to what would be the surface of a disk, and then take a coordinate system which would describe this zooming process. So you take the z direction itself is warped, non-like constricted. And then you say posit that your wave function depends on this warped coordinate, and you write out what is the Laplacian and Axion functions of the squeezed coordinate, which describes its limit. And the mind-blowing thing is that the Laplacian looks like a spherically symmetric solution, but in d dimensions, where here d is the amount by which you've squeezed the z coordinate, which corresponds to how much are you zooming into the xy plane. And if you go through this, you can construct through like near field limits, sewing it to a far field limit, Disclike solutions to the interacting system. And here's the dimensionless wave function you can get in the squeezed coordinates. This tells you how is the density changing as you move away from the xy plane. And what you find is that well within the limit of zooming in, you find these Disclike solutions. And this shows the density and the wave function. I'll mention that you do get constraints from Gaia, but they're actually not very interesting. Not very super strong. In the case of one of the dark disk papers, it's not super interesting on regular dark disks. But you can find details in that paper. Right, so another observable is worth discussing is strong lensing as a probe of ultralight dark matter and fuzzy dark matter, VECs, superfluids, this class of models. And this is a paper that I did with Michael Toomey at Brown and a number of collaborators, including some machine learning experts. And this appeared in both AppJ and it was an accepted submission to NeurIPS, which I thought was pretty neat. And the idea here was you simulate lensing images corresponding to different dark matter models with different characteristic substructure. And you think about think about this as like a fluctuation in the lensing image. And then you ask, how can a neural network is the path we actually went? You generate a huge pile of mock data and say, like, imagine Alice's T gave us a pile of data. How could we construct a system that would flag certain images for doing some sort of like traditional Bayesian MCMC analysis? So the picture is that it takes so much dedicated effort to analyze a single image, strong lens image, to get the substructure. So that basically the idea of this paper, which a few different authors have done since, is that we thought about what would be the pipeline. What would be really useful is if you had a multi-class classifier, which would flag certain images to do the analysis. And this comes out of so one of our collaborators, he runs the LHC machine learning group. And I mean, this is exactly what they do. They do triggering. LHC throws away most of their data. They have triggering, they have machine learning on the hardware that decides when you store the data. So this is a little bit like that. And for generating these, the mock data, we follow a procedure from a earlier paper by the Harvard group. So Cora's group at Harvard has some very nice papers on this. And so our approach was to generate this pile of data and try to build a multi-class classifier with some finite resources on a laptop that you could, and see how well can you classify strong lensing images corresponding to the underlying dark matter model. And the typical way to characterize the performance of a classifier is called the ROC curve, the receiver operator characteristic. And if you follow this diagonal, this is random guessing. So I'm playing false positive versus true positive. And a perfect classifier goes straight up and stays at 1 for the entire thing. So this is varying a threshold in your neural network. It's like a hyperparameter in your neural network. It tells you how well can I classify systems. And if you go right up to 1, this is as soon as I start classifying a perfect classification. And the way you can characterize this whole curve is to take the integral called the area under curve. And this has nice properties, like it's in a sense like diffeomorphism invariant. You can change coordinate systems in a neural network, and area under curve is unchanged. I mean, it's above my pay grade to explain that. But what's nice out of this, you can calculate the area under curve and say, as I change the fraction of the mass of dark matter halo, which is contained within substructure, when does my classifier fail? Which is to say, when's the area under curve fall below about 90%? That's a conventional thing to say your classifier has failed or is not performing very well. And the benchmark route we came up with, our constraint is that you need about 1% of a halo or in a cluster to be comprised of substructure in order for a classifier trained on a laptop to distinguish, say, a superfluid dark matter model from regular WIMPs. That was pretty neat. And I'll mention, so as motivation for other people to do similar things, I would say, so we used off-the-shelf neural networks here. We did not write a neural network from scratch. You used off-the-shelf pre-trained neural networks, and because of things like transfer learning, which are above my pay grade, but off-the-shelf neural networks perform extremely well to any physics problem you want. So it makes it very accessible to physicists who are new to that field, at least make some incremental and interesting progress. And I'd say that's what we did. It's incremental, but interesting progress. Right, the final observable that I want to talk about is spinning cosmic filaments, rotation of the cosmic web. And so this is denoting that this is simulation and this is data is something I do in public talks. You don't need me to tell you that this is not data, which is like a neat question that gets asked in public talks. But who would be taking that data to observe to make this picture? There's a very recent Nature paper, and I'm aware that Nature papers are always wrong, but let's take that Nature paper at face value and ask what would it imply, which I think is a well-motivated thing to do. We can't just always assume that every Nature paper is wrong. Like, what the hell would we, like, what we'd be concluding is wrong with academia at that point. And thinking about this in the context of you have some distribution of vortices within a filament. And so the data in this image is shown with the black dots and error bars. So that in this image, you're looking down, here's a filament coming like this, and you're looking down the axis. And this is the data here is averaged over thousands of filaments. And you look down the barrel of the gun, if you will, and think about if there's a net rotation, things should be moving this way here and this way here. And that tells you that the whole thing is moving this way. So this pattern, if you went like whoop, 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 that would describe a rotation. And it falls off at the edges where things stop being impacted by whatever's going on in the center of the filament. And this is, we're looking at the rotation of galaxies about the axis of a filament. And this is the data from the Nature paper, which is super exciting. And it's averaged, this is averaged over thousands of filaments. And so what we did was say, take a population of vortices, and that can generate a net rotation of, and these carry the angular momentum of the velocity field of the dark matter that surrounds this region. And so, like, one thing that's really interesting, I guess, if you take a population of vortices, so while the velocity field outside individual vortex falls off like 1 over r, if you get a collection of vortices, you can actually get like long range rotation. And this is discussed, like the small amount of math details I needed to show this is in the paper. So here, this is an image, and this is a megaparsec scale. So the vortices of these red dots are blown up, so see them on this picture. They have some distribution of vortices, and then this is the velocity field that they generate.
Presumably, there's the same amount going one way or the other way. So how do you?
Now, so assumes a net.
I'm just asking for the data.
Yeah, so that, but you can say, there's a separate question which is much more controversial. Is there a net rotation to the universe, which I think is crazy. So yeah, so this would imply that a filament is rotating in some direction. That implies there's a net angular momentum. So there's a net number of vortices which are driving this. So I mean, you take that
I don't understand the left one. You said that the points are data.
Yeah.
What kind of data?
You look at galaxies and galaxy clusters rotating around. Take the axis of the filament, and you like track the velocities of galaxies.
Yeah, but then you said it was stacked over many filaments.
Yeah.
But presumably some of them go one way, some of them.
Yes. So I believe that
zero. So how is it?
Yeah. So I believe the data analysis method was to flip it if necessary. Like look down the axis. So change like forms of transformation on the data so that you can look about the axis, and then flip it if necessary to see that the rotation will be one way or the other. And maybe there's a discussion to be had there whether how kosher that procedure is. Maybe, but let's just take for the motivation for the purposes of this today that it's arbitrary, the convention of if it's going one way or the other, but they do take each filament and flip it if necessary to see is it going one way or the other. Because the question they wanted to ask are, on average, are filaments rotating? And it's arbitrary where what will be the orientation of that filament.
Is there like prediction from simulations?
So the simulations are ambiguous. about. There's some evidence that you can get rotation for WIMPs, but to explain in the paper there, it's like impossible to get these in just regular old, say, fuzzy dark matter, except, okay, well, let me bracket that with saying, you can get, there's actually a huge value for saying vortices and fuzzy dark matter, but where it has to come from is things like vortices, or it can also come from interference. You can have point-like vortices, but you need some net angular momentum for you to get some net circulation of the field. So the most natural thing is angular momentum supported vortices from some net rotation of your condensate. Wait, your question was, there's simulations which show some vortices in things like superfluids, but this is all like very current.
No, like lambda CDM rotations, lambda CDM simulations, you can just take filaments and try to do.
So right now it's not clear if lambda CDM would give megaparsec scale rotation.
So
And even if it did,
how much of a filament do you take for this thing? Is it like a little region? Is it a long region? It's part of some, you know,
it's a long region. It's like average.
Some in different size. So how do you?
Yeah. So they average over the length of the filament for filaments of all different sizes.
The x-axis.
Yeah, so maybe let's talk afterwards, and I'd be also interested to know what, you know, because it seems like you already have really good ideas for things that could be wrong with their analysis.
No, I've never heard of it, so I was just trying to.
Okay. So for us, even if lambda CDM could produce these, you can still ask the question, can ultralight dark matter produce these? Because if this data is real and ultralight dark matter can't do the job, does this rely on ultralight dark matter? So there's still I think, a well-motivated question to say, hey, what would this imply? If you believe ultralight dark matter is the model of dark matter, what would that imply in order to match their data? And even if their data turns out to turn into, instead of an observation, upper limit, then we can still translate our results into an upper limit on, for example, on the number of vortices and the possibility of condensation. And I guess the thing I'll mention here is this is two possible distributions of vortices, because there's some asymmetry in the data. I'm happy to get into that in more detail after the talk or later today, or even with the paper. And I should mention, this is a paper with Christian Gavinelli. He's going to be my first PhD student, and I'm super excited to work more with him. Right, so let's get to summary. And I'm actually I'm pretty impressed with myself that the timing is going as I had hoped, because that's pretty hard to do with a talk, particularly when this was in large part a talk that I put together specifically for this audience. Right, so the first part of this talk is meant to really emphasize that ultralight dark matter provides many distinct paths to cosmological condensed matter, which I think is exciting, and there's a lot of opportunities there. And those lots of opportunities there, that's motivation for junior people to work on this. And I would categorize the opportunities as like low-hanging fruit, high-hanging fruit, and then crazy, like insane ideas that may or may not work or are impossible. I mean, the low-hanging fruit is what I was hinting at before, thinking about the diversity of dark matter halos in models much like dark matter, studying it analytically in terms of you have equations to solve, go ahead and solve them. And then the other aspect of that is exploiting this complementarity with super heavy dark matter, asking what do these models, considered in their totality, actually predict or are capable of producing. Things that are high-hanging fruit would be numerical simulations, which is like far above my pay grade, I would say. And part of those numerical simulations would be to understand the properties and distribution of vortices. And even studying that analytically is really difficult. So that's like a great, multi-year project. I'd say that's a high-hanging fruit, not low-hanging fruit. And then there's certain crazy ideas. There's this thing in condensed matter that happens in 2 dimensions, known as a BKT transition, whereas you can go from having no vortices to having, there's the state having vortices paired up, paired, anti-paired, versus gas vortices. Could you have this if you compress your condensate into effectively 2D geometry, which is somehow confined to 2D by either self-gravity or interactions or something? I would say that's a crazy idea, which probably doesn't work. And then there's also an ASCFT, there's ASCMT. Could you use tools from ASCMT to understand dark matter? It would be like the coolest paper ever, but I think that's pretty speculative. Okay, so now I want to finish with like my final comment, which is sort of like this extra tidbit to this talk, which I think there's interesting connections to the Hubble tension, which is something that I've worked on pretty extensively with Misha and Matthias. We have a nice paper using their effective field theory of electrical structure to constrain certain resolution of the Hubble tension. And we can debate the aspects of this, the motivations and things, and how well the models fit the data. That's a great conversation to have. Let's, I'm gonna get into it a little bit. So this is a model of really dark energy performed by, I guess that's the first paper which really argued that this can resolve the Hubble tensions, right in the title, because I've been Pion and collaborators. And it has the like dubious credit of these being referred to as the least unlikely to be true in terms of models to resolve the Hubble tension. And that's for a variety of reasons. So the general picture though is you take some, seemingly benign axion and you write down some polynomial in the usual axion potential. And what that gets you is initially it's frozen on the potential. It's like dark energy, some constant energy density, and then it rolls down and starts to oscillate. And by having a minimum, which is locally not phi squared, but phi to the some power, you get that energy density in this field redshifts away super quick. So you hide it from the rest of the universe. So what you get is early amount of extra dark energy, and then you hide it from the rest of the universe by having this power be greater than 2. That's the idea. And it was at least claimed to be fairly successful. And why I'm actually still working on this is because what if the act results are true, which maybe not very systematic, but I think it's still exciting. So one of the things that I've worked on is thinking about the CMB in the context of this model. I think it's fascinating at the very least that, so the Planck data itself, my paper with Colin Hill, I was 2 minutes long Alexander was the first one to actually just do a fit the Planck CMB anisotropies. No, we had done that before for some reason. They were always just tossing in always just throwing in everything, including shoes. So we did the first fit of just Planck, and this allowed us to understand a bit of the CMB physics, which is also developed around the exact same time, of course, by Wayne Hu. And more recently, myself and Wayne and collaborators have a paper explaining this in terms of gravitational potentials, which is the fundamental way to understand CMB anisotropies. But the name of the game, how is it that a model, some alternative NCDM with a larger H naught can fit the CMB as well as NCDM? That's a true statement even in Planck, which is neat. It's not preferred by Planck data, but it can do like almost as good a job as NCDM with H naught is 72 plus or minus change, whereas the MCM with normal H naught is 68. So the recipe is as follows, and you can reproduce this in 5 minutes using our code. Which is that you add in this early dark energy, and it screws up a couple things, but notably, it screws up the first peak of the CMB. And this has to do with, it modifies the driving of the acoustic oscillations. And that plus closely related the early ISW effect. And so the change in Hubble constant is about 5%. This is about that benchmark as well. So the fix to this first peak is adding 5% more dark matter. All right, the first order thing you need to do to fit the CMB while raising H naught by tossing an extra dark energy component is you need to weight down those gravitational potential wells by adding in more dark matter. But the amount of dark matter you add in is about equal to the change in the Hubble constant. This is 5.7%. This is over 5%. Okay, but that still screws up the damping tail. And so what you need to do to get the damping tail correct, you shift NS right up to pretty much 1, which is, I think that's pretty interesting. There's been a couple papers on this. I think it's underappreciated that in alternative flamming CDM, NS could be 1. So in a sense, we haven't ruled out exact scale invariance, despite like, I think it's WMAT papers has a section titled ruling out S equals 1, which is sort of interesting that the MCDM cannot be the whole story. So there's more, the MCDM is a model, not a theory. There's more structure, there's got to be. So NS could be equal to much larger value in some alternative to MCDM. And once you do this, so there's other parameter adjustments that happen, but if you change just the dark matter and NS, you already get like, or 1% change from MCDM. So this is the parameter compensation that needs to happen. So okay, I only have 2 minutes left, but I promise I'll be quick. Let's ask how well does ED actually fit the data? So as I mentioned, so it can fit the CMB pretty much as well as MCDM. So what it actually gets you is new degeneracies in the fixed CMB. So this is from my paper with Colin and Michael Toomey and Sloan Alexander. So, okay, this plot is like hard to read from the audience, but this is a degeneracy with an H naught and the amount of dark energy you put in. So if you put in, if you raise H naught, you need to be putting in more of this new dark energy component that's only present in the early universe for some reason. But now to maintain your fit in the CMB, this degeneracy direction is also flowing along the amount of dark matter, right? So here it's hard to see, but lambda CDM flows this way and EDE flows this way. So in order to this raised H naught needs more dark matter. And now as I also increase NS, having this impact on astrophysical scale also. If you look at here, okay, oh my God, this is so impossible to read for you guys. But this is S8 versus H naught, the posterior and the fit to the primary anisotropies, like 2018. And you can see that it's tilted this way is the main point. And DES is like down here, and the SA H naught contour is perpendicular to lambda CDM, and it's flowing up. If you bump up H naught, you have to bump up S8. And then what you ask is when you throw in larger structured data, it breaks this degeneracy direction. You get one of the punchlines from Misha and Matisse's like extensive number of beautiful papers on BFT of LSS is that from the full shape data, you can get a pretty good measurement of the amount of dark matter in the universe, which is fantastic. And so it breaks these degeneracies. And what you get then is values of H naught, which are not so different from the NCDM. You're like, this is red in these plots is lambda CDM, blue is EDE. They're like pretty much near overlapping. And this is 2 papers, first with Colin and myself and Michael and Swan, and then the second, which is the EFT crew combined with our crew. I think it was a really nice paper and very fun collaboration. And then I also mentioned, we talk a lot about the interplay between CMB and LSS data in this recent paper I did with Wayne and his student Meng Cheng, who is right now going to do a postdoc at Penn. You should invite him to give a seminar here. And Colin and Colin's student at that time, Shinja. Okay, so one fix, and maybe you don't like too many tooth fairies. That's a phrase that Colin likes to use, too many tooth fairies. But one fix to this problem, which is that Tossen's early dark energy was clearly incompatible with large-scale structured data, is you put in some ultralight field to cut off the amount of power spectrum. And so that's worked out in detail by, it's sort of obvious, but to actually do the analysis is another thing. So these authors did the analysis and showed that indeed this is the case. And what I'm working on right now, and hopefully will appear very soon, is that this additional ultralight field naturally falls out of trying to construct a UV completion of early dark energy. So in particular, supergravity and string theory models for this early dark energy field, it's one component of a complex scalar. And the other component of that complex scalar, when you think of model realizations, is actually itself an ultralight field. And it's just like a regular massive field. It doesn't have this crazy cosine potential. It's in the right mass range to the axion of this paper, which I think is super interesting. And this goes back to my original point about Ultralight dark matter, that we should think about the structure of our theories and let the theories tell you what the predictions are, and not trying to force what you want onto the theory. All right, so that's it for today. Thank you for coming. This was fun. Enjoy the rest of the day. Fly to New York at 9 p.m. I'm happy to talk.
Thank you. Yes, Anand, please.
So as one of the authors of the original fuzzy dark matter paper, so you mentioned it's only then the cutoff of the power spectrum, but so in the fuzzy dark matter model, there's a close correspondence between the scale of what you talked about mostly, which is a nonlinear effect on cores of halos and so on,
Yeah.
and the cutoff the linear power spectrum. And observationally, it doesn't seem to be a cutoff at interesting scales. So all of these models that you talk about, how do they produce a cutoff in the linear power spectrum, or is that free parameter? Or
I think it's basically the same status, but you don't need to take the fuzzy limit at 10 to minus 22, right? So if you take 10 to minus 15, a lot of that, it's still ultralight dark matter, but it's not the fuzzy limit. And in that case, you're not really explaining the quark cost problem. You do have neat things like boson stairs. That's why I said I think Picasso models, while originally motivated in part by quark cost, is like distinct from that. That's one possibility. So you get similar phenomena, but it's exact same thing with say an axion. If you dial the mass, you change where the cutoff is.
But what you mentioned this last point about suppressing the power spectrum, not some other type of suppression, not a cutoff.
Yeah, so that's a setup where you're bumping it up and then suppressing it. So it's like some compensating factor. And you say you put in like 2%. That's also here. We're not saying 100. They're not saying 100% of dark matter to this.
Oh, okay.
So so the CME tells you in this range it's like less than 5% of dark matter or something. So that's an extra parameter, and I'm well aware of the saying that like with one parameter you can draw an elephant, and 2 parameters you can make it wag its tail. That's a fair point. So here they're saying you allow the fraction of dark matter that you have to float, and so it's that you get some suppression. So you have to bump up the dark matter, and then you like custom tune how much suppression you get by changing the mass and the fraction of dark matter.
More questions? Do we have questions from Zoom? Okay, then if not, let's thank Evan again.